In this paper, we explore various methods to enhance the efficiency and recall capacity of attention mechanisms in neural networks. We introduce an approach where softmax attention is approximated using linear feature maps, significantly improving efficiency by maintaining a fixed size for the recurrent state during generation. This method leverages the associativity of matrix products, allowing us to compute attention in constant time and space. We select feature maps based on the Taylor series to further enhance the model's recall capacity without increasing the computational complexity. Additionally, we implement sliding window attention to limit the recurrent state size effectively. This technique caps the recurrent state size and facilitates efficient modeling of local interactions through the use of small window sizes. By adjusting these window sizes based on hardware specifications, we can control memory consumption and ensure efficient computation. To achieve high recall accuracy, we combine the strengths of softmax approximating linear attention with exact softmax attention within small sliding windows. This hybrid approach allows us to recover most of the full softmax attention's recall accuracy while significantly reducing latency. Our experiments demonstrate the effectiveness of this method in balancing efficiency and recall capacity, showcasing its potential in various applications. We also employ the Taylor series feature map to expand the recurrent state size without adding extra parameters. This choice is validated through comparisons with alternative feature maps, where the Taylor series feature map shows superior performance in improving recall capacity. This method achieves high recall with fewer parameters, highlighting its efficiency and effectiveness. Lastly, we focus on optimizing computation through EO-aware algorithms, especially during the prefill and next token prediction stages. By developing algorithms that compute feature maps and causal dot products in fast memory, we reduce data movement between high-bandwidth memory and SRAM. This approach results in higher throughput and faster prefill times compared to existing implementations, demonstrating the potential of our methods in enhancing the performance of neural network attention mechanisms.